Okay, so we're just going to spend a few minutes here just catching up on lesson 3 here about optimization problems. We're going to finish the one that we didn't finish in class. And then I'm going to take a look at one or perhaps both of these ones from lesson 4. As I said earlier, this unit is really about optimization. It's all about using this technique here from lesson 2, maximum and minimum on an interval, and simply taking that same idea and applying it to a series of different situations. So we're going to go move ahead here to lesson 3, and we're going to look at this one here about the open top metal can to be made to hold 100 milliliters. So let's see what we can do with this one. Okay, so I was saying in class, the first thing you want to do is create a relationship is what is it we are optimizing. And of course in this case we are optimizing, it will minimize the amount of metal required, so we want to minimize amount of metal required. That would be the surface area, and the surface area of a can is equal to so I mean, but what do we have? We have you have to think of the shapes that a cylinder is created from. It's created from a top plus a bottom plus the wall, right? The wall that sort of wraps around it. Now, the top and bottom are both circles. The wall is a rectangle, right? And picture the idea of the net diagram. So the net diagram looks something like that. You have a top, a bottom, and then a wall that wraps it. For the dimensions of the wall would be the circumference times the height, and of course the top and the bottom would each be a pi r squared, right? So in our case, we're looking at an open top metal can, so that would imply that we don't actually need the top. So for our case, the surface area is just going to be the bottom plus the wall, in which case we get the equation surface area is equal to pi r squared times, pi r squared plus 2 pi rh. And 2 pi rh, where is this coming from? 2 pi r is the circumference of the circle, which you can imagine would have to be equal to the length of this part of the rectangle. This dimension of the rectangle would have to wrap completely around the circle. So that's how we're getting that one. And then the height would simply be the height of the can. So we have surface area is equal to pi r squared plus 2 pi r h. Now, once we have the thing that is to be optimized, the second thing we look for is what is the constraint. So some sort of constraint needs to occur here, because otherwise we would just make a can that was just a millimeter tall and it would not use very much material. But our can needs to hold 1,000 milliliters. So the constraint equation is usually going to be a different quantity, right? So our first quantity was surface area. Our constraint equation is the volume of the can must be 1,000 milliliters. Come up with an equation. Volume equals 1,000. We know that for a cylinder, even if the cylinder doesn't have a top, of course the top is not really going to influence how much space is on this cylinder, because you could still fill it all the way to the top even without a cap on the top of your cylinder. The volume of a cylinder, we know, is equal to the area of the base, which is pi r squared, times height. So what we need to do now, okay, so we have an equation that we want to optimize, surface area. We have an equation that constrains what we're allowed to do, which is volume. And what our third goal here is to construct a function using, so let's put it this way. Let's say isolate a variable from the constraint equation. The problem with what we're trying to do here is we're trying to optimize surface area. Surface area has two variables, right? There's the radius and there's the height. You can't optimize something with two variables at the same time, so this is why we use the constraint equation to basically replace one of the variables. So we come up with the idea that 1,000 is equal to pi r squared h, which means that h is equal to, we get our 1,000 1,000 divided by pi r squared. Okay, now what this lets us do is create a function using one variable, which can be, let's say, create a function out of the first equation using only one variable. So our first equation was up here. Surface area is equal to pi r squared h plus 2 pi r h. And now I can go ahead and say, well, I don't need to write h anymore. I can use my equation that I know h is equal to. This comes from up here. And I can stick that in, right? I know h is equal to this, this thing here. I'll just give it a different color so we can recognize the substitution. Key difference here is that what I just did is construct a function, right? Because surface area is now a function, right? So surface area function. The input is simply r, which is the radius, and the output is the surface area of the can. And so we've managed to basically bake in the height into this second equation, and we can now go ahead and have an equation we can actually optimize. So what we want to do now is take a look at this equation and go ahead and optimize your equation. So we need to check the extreme values of the domain and any critical points. The domain in this function is actually not that easy to understand. Find the dimensions of the can that will minimize the amount of metal. Assume that the bottom and the sides are made from the same thickness. So it doesn't really tell us any information. What we could conclude is that r is equal to, obviously 0 is less than or equal to r. We know that. We don't really have a sense of what the maximum radius could be, since with a height of 0 you could have an infinitely large radius. So let's say we don't really have a second boundary for this. Let's just say we have the one boundary. We know r has to be bigger than 0. We don't know any better than that. So we have two possibilities, right? Surface area of 0 could be our ideal, or surface area of any critical point could be a candidate. So what we need to do here is we need to find the critical points. So critical points, remember, we have our function. Just going to quickly copy this again. Our function's here. Okay, we are going to simplify. So we'll just take another quick look at this and simplify it. Of course, we have a pi r here, which we can cancel out with the pi r down here. So this pi, for example, we can strike, and this pi we can strike, and this r we can strike, and that would mean that this r squared here we can strike as well. So we get something a little bit simpler to look at now, right? So that pi is gone, r is gone, the r on the bottom is no longer squared, it's just r, this pi is gone, and we have 2,000 instead of, so 2,000 over r. Okay, this equation is now what it is that, we've just got our surface area function. We need to differentiate it, so we'll quickly do that. So we take the derivative. The derivative here would be 2 pi r. We drop the exponent. And then over here, let's just take a minute to picture this as 2,000 r to the minus 1. Sorry, r minus 1. And of course, the derivative then becomes negative 1 times 2,000 r to the negative 2, right? And so our surface area function not sure why that r up there just disappeared on me, but okay, our surface area function, we can sort of write it out a little more cleanly as this. So we get negative 2,000 over r squared. And that's basically the equation that we're now going to set to 0. And this is where we're going to reveal any potential critical points that we would need to answer. Of course, when we do this, we're going to want to multiply everything by r squared so that we can get rid of times r squared, that denominator, right? We don't want any denominators. Of course, the denominator being 0 could be a problem because the denominator being 0 would be a place where that has an asymptote, but we're not going to worry about that because r being 0 is already a number we're checking. Remember, it's part of our interval from before, so r being 0 is not really an issue for us to deal with. And we end up with an equation that just goes 0 equals 2 pi r cubed minus 2,000. And whatever the solution to this is, that's going to tell us the critical point. So to finish this off, we just need to isolate r cubed, so we get another equation, 2,000. 2,000 is equal to 2 pi r cubed, and therefore r, so 2,000 divided by 2 pi would be equal to r cubed. Oops. Equals r cubed, and therefore 2,000 over pi cube rooted is going to be our answer. Okay, so equals r, and we'll just quickly take the cube root here. Okay, so cube root 2,000 over 2 pi is our r. This would be the other critical point. So to answer the question, optimize, so it's optimized at SA of 0 or SA of this critical point. And let's just quickly find each, and we can analyze it from there. So the surface area function, to go back, was this, right? Pi r squared plus 2,000 over r. So let's just quickly draw this. SA, I'm going to use x here in GeoGebra, so 2 pi x, sorry, I just got mixed up there. Pi r squared, sorry, not 2 pi r, mixed up. Pi x squared plus 2,000 divided by x, right? And this was our surface area function that tells you what what the function, what the surface area is, depending on what value you've put into the equation. So one candidate we said was SA of 0. So let's say SA 0. And the surface area there is infinity. And, what is that trying to tell you is that if you try to plug in a radius of 0, of course you can't, you could make an infinitely large rectangle, right? To think back to our cube for a second, think back to our picture. If I don't have a radius, if there's no circle here, then this rectangle has to be infinitely large to create any volume at all, right? Because it has no height. It would always have a volume of 0. So it makes sense that when r is 0, you don't really get a surface area that means anything. And so, of course, we're going to reject SA of 0. That doesn't make sense. Other option is to think about the critical point that we got. And we know, so let's say the radius of this critical point we know is equal to 2,000 divided by 2 pi, and all of this raised to the power of 1/3 because it's a cube root, right? And so this suggests that the ideal radius for our can is 6.83. If we check the surface area of 6.83, so here we arrive at a surface area of 439.38, right? And what this is suggesting to you is that the best possible can you can create, right, the one that will have the smallest radius, the one that will have the smallest surface area, is a can that has a radius of 6.83. When you examine our graph of our function, which is here, you see that it has a clear minimum, only one critical point, right? And if I graph this point, R of C and A, you notice that, that's a point where if we drew the tangent A and SA, you get a flat tangent, right? So we found the minimum, the absolute lowest possible surface area, and thus we have optimized this particular problem. We know the correct dimensions to minimize surface area.